Okay, welcome back. Today we're going to be doing, we're going to be continuing on, right? We already did SN1, SN1, and we already did SN2 reaction mechanisms. So remember substitution, nucleophilic substitution, unimolecular. So this one, right, was tertiary carbons, and nucleophilic substitution 2, which was bimolecular. That's what the 2 is, bimolecular. And this was primary, and this one had the inversion. So if you don't remember any of that, I recommend you rewatch those last 3 videos. And then we'll continue from here. So today, what we're going to be covering is we're going to be covering factors affecting the rate. So it's factors affecting the rate of nucleophilic substitution. So we're going to be doing this in multiple videos. So basically, this will just be the first one. So the first one, one of the most important, of course, the most important for tertiary SN1 mechanism is the identity of the halogen. So it's the identity of the halogen. So that means, basically, if we have it bonded to fluorine, if we have it bonded to chlorine, if we have it bonded to bromine, if we have it bonded to iodine. So it depends on the identity of the halogen. And this one, today I'm going to try to explain this, but what we're going to have to realize, though, really quickly, is that one of these breaks the trend. We've got all of them follow the trend completely, and then we've got this guy right up here that completely breaks the trend of all of the information that I'm going to be presenting. So the most important thing to remember for this factor is that the carbon fluorine bond strength is the greatest, is the largest, compared to a carbon chlorine, carbon bromine, or carbon iodine bond. So this is the important thing to remember, is that all the effects that we're going to be talking about, all the electronegativity differences, the size, the presence of the resonance structure, the strength of the acid or the base, all of this relates somewhat to the carbon fluorine and also the fluorine hydrogen bond strength. It's going to be dealing with the bond strength of these two versus the polarity. Whereas the rest of them, it's just going to be dealing mainly with basically with polarity and size. So okay, so basically what we're going to be talking about today is how the identity of the halogen affects it. So how that is that bond strength decreases as we move down the halogens. So this is a more simplistic way of looking at it. So bond strength decreases. So carbon fluorine is the strongest bond, carbon chlorine is the second, carbon bromine is the third, carbon iodine is the fourth, which means that iodine is a better leaving group, can leave, right? It's got a weaker bond between iodine and carbon, so it can leave. So our leaving group, which makes the best leaving group, is that iodine is better than bromine, is better than chlorine, is better than fluorine. So that's basically our leaving group. This is what we need to know. And this is, of course, what we need to memorize in this case. So if you can imagine, right, we've got, if we'll just say we have, iodomethane. So basically all you need to know here is that iodine likes leaving more than fluorine. So if we had some sort of solution with fluorine ions in here, he would attack, he'd transfer up, this would be the SN2 mechanism, and then we'd have fluoromethane instead, plus iodine. And this is basically, right, just this fluorine forms a stronger bond. If we were to put them into solution, the one that reduces the overall energy of the system is going to be the preferred product. So since fluorine carbon bond is stronger than iodine carbon bond, we are going to have a delta H, which is negative, and we are going to, release some energy. So the bond strength decreases as we go down the halogens. And basically, this affects both, right? This affects the SN1 mechanism, where the rate is equal to the rate constant multiplied by the haloalkane concentration. And this affects the SN2 mechanism, right? SN2 mechanism is that the rate is dependent on K, the haloalkane, and the concentration of the nucleophile. So the concentration of the fluorine, if we add in a bunch of fluorine, right, the chances of it coming in the right location is higher. If we decrease the concentration, the chances of it coming in and running to this molecule in the right configuration is lower. And also the concentration of haloalkane, right? We've got a bunch of these. The chances of fluorine running into the right location is more. If we get, less, the chances of it coming in are less. So basically, a way to kind of consider this is that weak Lewis bases are the best leaving groups. So weak Lewis bases. So what this means, right, is if something is a stronger stronger Lewis acid, it basically forms weaker bases. A weak acid produces a stronger base, and a strong acid produces a weaker base. So the way that you can kind of consider this is if we look at HI, we look at HBr, hydroiodic, hydrobromic, and hydrochloric acid, and we look at their pKa values. If we look at their pKa values, we see that hydroiodic acid has a negative 11 pKa value, has a negative 9 pKa value, and has a negative 7 pKa value. We're leaving fluorine out of this because fluorine is actually a weak acid, but it undergoes different reactions that causes it to be extremely corrosive. So although it's a weak acid, I believe it's pKa HF. The pKa is something just above 3. So basically we see as we go, from iodine to bromine to chlorine and fluorine, the pKa, the more, this is just for those of you who didn't go into the acid-base unit as much as you probably should have. As the pKa value decreases, the acidity increases. So the smaller the value, the better it is at just having that, forming that H plus in solution. So hydrofluoric acid, you can see it's a bigger number than all the other ones. So it's actually a weaker acid than all the other ones. So the stronger the acid that the halogen forms, the weaker the base and the better the leaving group. So what this means is that, your base rate here is I minus, which is a rather stable, good leaving group. HBr it has the exact same structure in the end, but it's a worse leaving group, and this hydrofluoric fluorine will be our worst leaving group. So and that's because of the bond strength. That's because of the carbon-fluorine bond strength and the fact that it is a weak acid. But just remember that just because it's a weak acid doesn't mean that it's extremely reactive, because it's got that fluorine ion, and that fluorine ion loves forming bonds. And it forms very, very, very stable bonds. So it's corrosive in a different way than acids typically are. So I'm just going to erase maybe this top part right up here, and then we're going to continue going just a little bit. But right, the important part for you to know, fluorine is the worst leaving group, and iodine is the best leaving group. So aside from that, ways to kind of describe this, the identity of the ways to describe these trends that we're seeing. We can either say, the weaker the Lewis base, the better the leaving group. So basically, the stronger the acid, it forms the weaker the base, and the weaker the base is more stable. But we've got some rules that we can follow. And rule 1 is typically, as electronegativity increases, as electronegativity or electron density increases. Let me just, I'll write electronegativity. As electronegativity increases, typically basicity decreases. So hopefully this makes a little bit of sense, right? As the atom starts to want more electrons, its ability to donate those electrons is less, so it's a weaker base. So right, so fluorine is very, very electronegative. But so this is where I'm saying that the trend, the rules don't always apply. So fluorine is the most electronegative, but it's not the weakest base because the bond strength is much higher. Whereas in this case, the bond strength is much lower. So the trend basically starts from chlorine to bromine to iodine in this case to follow this rule. And like I said, that's just because more things are happening with fluorine than what we actually need to know in IB. So the second one, so this is basically continued, right? We know chlorine is more electronegative than bromine. So chlorine electronegativity increases, basicity decreases. So chlorine is a weaker base, a stronger base, and the strongest base. And if it's the strongest base, it means it's the basicity decreases. The ability to want to donate decreases as we go up. Okay, so the second one, basically what we're going to be covering, as size increases, basicity decreases. So right, as we go down this group, the size is increasing. So the ability of it to donate electrons is worse and worse and worse. And like we said, weak bases are the best leaving group. So if the basicity, as the size increases, the ability to act as a strong Lewis base decreases, which means that iodine is a better leaving group than bromine, which is a better leaving group than chlorine. And third, our trend is that resonance. So this is going to be an important one. If the leaving group can form a resonance structure, then it's a better leaving group. So basically, these are the trends that we're gonna have to learn, and like we showed, right? This one, it's not always true. The second one is a good way to think about it. As size increases, it becomes a better leaving group. The size increases, the basicity, the how much it wants to donate, that lone pair decreases, and when it decreases, it means that it's happy just taking it and being stable. The more it wants to donate it, the worse of a leaving group. So chlorine is a worse leaving group than bromine, which is a worse leaving group than iodine. And the third one is definitely true, but we won't be dealing with that because we're typically dealing with haloalkanes. And that means it must have a halogen, and halogens don't typically have the resonance structures. So okay, hopefully this was somewhat useful. I'll see you in the next lesson.